Every single decision you have ever made might have forged an entirely separate world. This is the staggering premise of parallel universes, a concept perched on the edge of known physics and boundless imagination. By the end of this journey, you will have explored 25 distinct realities that could exist alongside our own, from the rigorously calculated to the wonderfully bizarre. We will venture into cosmic bubbles where time runs backward and descend into black holes that birth new creations. What fundamental truth about our own existence might these shadow worlds reveal? Our journey begins with the most scientifically grounded, yet mind-bending possibility of them all. It is a reality where every choice, no matter how small, is not a choice at all but a branching point. This is the quantum many-worlds universe. In the 1950s, a physicist named Hugh Everett proposed a radical solution to a strange puzzle in quantum mechanics. At the subatomic level, particles exist in a haze of probability, a blur of all possible states until they are observed. The act of observation, the measurement, forces the particle to pick a single reality. Everett asked a simple, profound question. What if that particle does not actually choose? What if instead the entire universe splits? In this interpretation, every single quantum event, from the decay of a radioactive atom to the path of a photon of light, causes reality itself to fracture. Each possible outcome plays out, but in a newly formed parallel branch of existence. The universe you experience is just one thread in an infinite, ever-expanding tapestry of possibilities. This means there is a version of you who, at this very moment, decided to stand up and get a glass of water. There is a version who won the lottery last week, who became an astronaut, who chose a different career path decades ago. And yes, there is a version of the world where you were never born at all. These are not mere fantasies in this model. They are concrete, physical realities, forever separated from our own by the uncrossable gulf of a quantum split. The many worlds interpretation elegantly sidesteps the so-called measurement problem in physics, removing the need for a special observer to collapse reality into being. It suggests a cosmos of breathtaking, almost paralyzing abundance where everything that can happen does happen somewhere. But if every possibility is realized, what does that say about the path you are on right now? Is it special, or is it just one among an infinite number of equally valid stories? Yet for all its splendor, the many worlds universe feels strangely personal, a reflection of our own choices. The second possibility is far grander, a cosmic architecture on an unimaginable scale. This is the inflationary multiverse, and it suggests our entire cosmos is merely a single bubble in an endless, frothing sea of creation. To understand this, we must rewind to the very first moments after the Big Bang. According to the theory of cosmic inflation, the newborn universe underwent a period of hyper-fast, exponential expansion, stretching a speck of space smaller than an atom to a volume larger than our observable universe in a fraction of a second. This elegant idea solves several major puzzles in cosmology, but it comes with a staggering implication. What if that inflation never truly stopped everywhere? The concept of eternal inflation proposes that the driving force behind this expansion, a field of energy permeating space, only decays in certain regions. Picture a pot of water coming to a boil. Bubbles form randomly within the roiling water. In our cosmic analogy, each of those bubbles is a region where inflation has stopped, allowing for particles, stars, and galaxies to form. That bubble becomes a full-fledged universe like our own. But outside that bubble, the inflationary process continues at a furious pace, eternally creating more space, and within that new space, more bubbles will inevitably form. Our universe, in this view, is just one bubble in an infinite, ever-growing cosmic foam. The truly profound consequence is that each of these bubble universes could be fundamentally different. When inflation ends in a region, the energy of the inflating field is released, setting the stage for the laws of physics as we know them. But if this process happens differently in different bubbles, the resulting universes could have different strengths for gravity, different numbers of spatial dimensions, or even different sets of elementary particles. Some bubbles might be stillborn, collapsing instantly. Others might be filled with nothing but chaotic radiation. A rare few, like ours, might have the precise, delicate conditions needed for complexity and life. This framework does not just give us copies of our own world with different historical outcomes. It offers a vision of a multiverse where the very rules of reality are up for grabs, a vast experiment in cosmic possibility. If our bubble is just one accidental paradise in an infinite chaotic sea, what does that say about the laws we consider fundamental? Are they written in stone, or are they merely the local bylaws of our quiet neighborhood in a much wilder metropolis? But what if these other universes are not distant bubbles or quantum branches? What if they are right here, all around us, separated by a gap thinner than a sheet of paper, yet utterly impossible for us to cross? This brings us to the third parallel reality, the brane multiverse, a vision born from the most ambitious attempt to unify all of physics, string theory. In this framework, the fundamental particles of the universe are not tiny dots, but unimaginably small, vibrating loops of energy, strings. And for the mathematics of string theory to work, it requires more than the 3 spatial dimensions we experience. It needs 10 or even 11. We do not perceive these extra dimensions because they are curled up or compactified at scales far smaller than an atom. But one radical idea suggests that not all of these extra dimensions are tiny. Imagine our entire 3-dimensional universe, all of space with its galaxies and stars, is actually a 3-dimensional membrane, or brane for short, floating within a higher dimensional space called the bulk. In this picture, we are stuck to our brane like ants crawling on the surface of a vast leaf. We can move forward, backward, up, down, left, and right, but we are utterly unaware of the greater volume that surrounds our leaf. Now picture another leaf, another 3-dimensional brane, floating parallel to our own in this higher dimensional bulk. It could be mere millimeters away in a direction we cannot point to, a direction that does not exist in our reality. A whole other universe with its own stars, planets, and perhaps life, existing right next door, yet forever invisible and unreachable because we are trapped on our own membrane. The implications are staggering. A collision between 2 such branes drifting through the bulk could have been the cataclysm that sparked our own Big Bang, a titanic clash of realities that birthed our cosmos from the ashes of another. This idea even offers a potential answer to a long-standing mystery in physics. Why is gravity so astonishingly weak compared to the other fundamental forces? A magnet can lift a paperclip, defeating the gravitational pull of the entire planet Earth. In the brane model, one explanation is that while particles like electrons and quarks are strings whose ends are pinned to our brane, the carriers of gravity, called gravitons, could be closed loops. These loops would not be confined to our brane. They could drift off into the bulk, leaking their strength away into the higher dimensions, which is why gravity feels so diluted in our 3-dimensional world. So, the force that holds galaxies together, that sculpts the cosmos, might feel feeble to us only because we are seeing a shadow of its true strength, a whisper of a force echoing from a realm we can never touch. The vision of a brane multiverse suggests other realities could exist alongside us, separated by a hidden dimension. But there is another, more ancient and cyclical possibility, where parallel worlds are not neighbors in space but ancestors and descendants in time. This is the cyclic universe, a cosmos with no true beginning or end, only an endless, rhythmic heartbeat of creation and destruction. Imagine our entire cosmic history, from the Big Bang to the distant future, as a single, magnificent breath. First, an explosive outward expansion as space unfurls and galaxies rush apart. Then, after trillions of years, a long, slow inward sigh as gravity finally wins its cosmic tug of war, pulling every star, planet, and speck of dust back together. This is the concept of a big crunch, a mirror image of the Big Bang where the universe collapses into an unimaginably hot, dense singularity. In the traditional view, that would be the end of everything. But the cyclic model proposes something far more extraordinary, that this singularity is not a final end, but a cosmic reset button. From that point of infinite density, the universe rebounds in a new Big Bang, a phoenix born from its own ashes. Our universe, in this view, is just the current cycle in an infinite sequence. Each cycle, or eon, would be a self-contained universe with its own timeline, its own formation of stars and galaxies, and potentially its own story of life. When the collapse happens, the intense heat and pressure of the Big Crunch could effectively erase the information of the previous cycle, scrambling the cosmic deck. Then, as the universe bounces and expands anew, the fundamental constants of physics, like the strength of gravity or the mass of an electron, might be randomly redealt. Each new cycle would start with a slightly different set of rules. In one eon, gravity might be so strong that stars burn out in mere millions of years, leaving no time for planets to form. In another, the nuclear forces might be too weak to forge the carbon essential for life as we know it. Our universe, with its seemingly fine-tuned constants that allow for complexity, would then be just one lucky roll of the dice in an endless series of cosmic throws. This idea transforms the concept of parallel universes from a spatial one into a temporal lineage. The parallel realities are not out there but came before and will come after. We are living in one chapter of an infinite book, where every chapter tells a vastly different story governed by different physical laws. The echoes of a previous universe might even be detectable in the faintest whispers of radiation left over from our own Big Bang, a ghostly signature of a cosmos that once was. If this cyclical model is true, then every ending is merely a prelude to another beginning, and our entire existence is a single note in a symphony that has been playing forever. But what if the cycles are not perfect resets? What if information, some echo of structure, somehow survives the transition? Could the galaxies of a future universe bear an uncanny, faint resemblance to our own? The idea of a cyclical cosmos offers a lineage of universes, each born from the death of another. But there exists a concept so all-encompassing that it makes even an infinite cycle seem like a small story. This is the mathematical universe, a hypothesis proposed by physicist Max Tegmark that forms what he calls the level 4 multiverse. Its premise is deceptively simple, yet its implications are the most staggering we will encounter. Tegmark proposes that every single mathematical structure that is logically consistent corresponds to a physical reality. In other words, if you can describe a universe with a self-consistent set of mathematical equations, that universe exists somewhere in the ultimate ensemble of all possibilities. Our universe, with its 3 dimensions of space, one of time, and its specific laws encoded in equations like Einstein's relativity, is just one mathematical structure among an infinite sea of others. This is not about mathematics merely describing reality. It is about mathematics being reality. The cosmos is not just written in the language of mathematics. It is mathematics in the same way that a triangle is not just described by geometry. It is geometry given form. Within this ultimate multiverse, the variety is not just in historical events or physical constants, but in the very fabric of existence itself. There are universes where space has 5, 10, or 100 dimensions, curled and folded in ways we could never visualize. There are realities where gravity is not an attractive force, but a repulsive one, where objects naturally push each other apart in a perpetual cosmic explosion. There are worlds where time is not a single arrow, but a 2-dimensional plane, or where it flows backward from our perspective with cause and effect reversed. Some mathematical structures might describe universes that are static and eternal, with no time at all, just frozen, beautiful patterns. Others might be so chaotic that the very concept of a stable object, like a planet or a star, is mathematically impossible. The Level 4 multiverse contains every universe that the human mind can conceive through mathematics, and an infinity more that we cannot. It contains worlds made of pure symmetry, universes that are nothing but intricate knots of topology, and realities governed by laws so alien that calling them physics would miss the point entirely. The philosophical weight of this idea is profound. It suggests that everything that is not mathematically impossible exists. Every coherent fantasy, every consistent science fiction setting, every bizarre dream that obeys its own internal logic corresponds to a real, physical universe somewhere in the multiverse. The dragons of legend, the worlds of fiction, the unimaginable realms beyond human thought, they are all as real as the chair you are sitting on, simply because a self-consistent mathematical structure can be conceived to describe them. This dissolves the boundary between imagination and reality in the most fundamental way possible. It also presents a deep answer to the question of why our universe seems so mathematically elegant. The answer, in this view, is that we are asking the question from inside one particular mathematical structure. We could not find ourselves in a universe whose laws were inconsistent or incoherent, because such a place could not support complex observers like us to wonder about it. Our existence is a filter selecting us into one of the mathematical structures that allows for conscious life. This idea pushes the Copernican principle to its absolute limit. Not only is our planet not special, our galaxy not special, our universe not special, but our very laws of physics are not special. They are simply one page in the infinite library of mathematical existence. If this hypothesis is true, then the quest to find a theory of everything for our universe is not the quest to find the fundamental rules of reality, but merely to find the address of our particular mathematical neighborhood in a cosmos without end. The ultimate mathematical multiverse suggests every coherent reality exists, but it raises a disturbing and intimate question about our own place in the grand scheme. What if our universe, with all its mathematical elegance, is not a fundamental reality at all, but a construct? This leads us to the sixth parallel possibility, the simulated universe. The idea that our cosmos is an artificial creation, a sophisticated simulation run by a vastly more advanced civilization, has moved from science fiction into serious philosophical debate, largely due to the work of philosopher Nick Bostrom. His simulation argument presents a stark trilemma, three propositions, at least one of which he argues must be true. First, almost all civilizations at our level of technological maturity go extinct before developing the capability to run complex simulations. Second, if they do survive, almost none are interested in creating vast, detailed simulations of their own ancestral past. Third, if a significant number do run such simulations, then the number of simulated minds would vastly outnumber the minds in the original, base reality. In that case, the odds are overwhelming that you and I are not in the original reality, but in one of the simulations. Think of it like this. If a future civilization with computing power trillions of times beyond ours decided to run high-fidelity simulations of its own history for research, entertainment, or education, they could run millions, even billions of them. The number of simulated beings across all those programs would be astronomically larger than the population of the single, original civilization that built them. Statistically, any conscious being picked at random from the total pool of all conscious beings that have ever existed is far more likely to be a simulation than a biological entity in the base reality. This forces us to confront the nature of the world outside the simulation. What is base reality like? It could be a universe with completely different, perhaps more fundamental, physical laws, where beings of pure information or energy have mastered reality engineering. Their motivations might be utterly inscrutable to us, as alien to our thoughts as our intentions are to a character in a video game. And if they can create one simulation, why not many? This opens the door to layers upon layers, a cosmic nesting doll of realities. Our simulated universe could itself contain simulated civilizations that, upon reaching a technological singularity, create their own simulated universes, and so on ad infinitum. The true depth of reality could be unknowable, a regression of worlds within worlds. The most haunting question, of course, is whether we could ever detect the simulation. Are there glitches in the matrix or programmed limits that give it away? Some have pointed to fundamental constants like the speed of light as a potential candidate. It is a universal speed limit, a hard-coded ceiling for information processing in our cosmos, not unlike the maximum rendered distance or processing speed in a computer game. Quantum weirdness, like the way particles exist in superposition until observed, could be seen as a clever programming trick to save computational resources, only rendering the fine details of reality when someone is looking. Even the discrete, pixelated nature of space and time at the Planck scale could be the underlying resolution of the simulation's code. If this hypothesis is true, it recontextualizes everything. The search for a grand unified theory of physics becomes the search for the source code of our particular simulation. The mysteries of consciousness become questions about the nature of the simulated mind. Our entire history, our struggles and triumphs, our art and love, could be data points in an experiment we cannot comprehend. This does not make our experiences any less real to us, but it does cast a strange, digital shadow over the cosmos. If we are living in a simulation, what happens when the beings running it decide to shut it down, or worse, simply lose interest? The unsettling possibility of a simulated reality forces us to question the very substance of our world. But what if the answer to a cosmic mystery is not a digital illusion, but a material one made of a substance that is right here, yet forever beyond our reach? This brings us to a parallel reality woven into the very fabric of our own, the mirror matter universe. Imagine a perfect, shadowy twin to every particle that makes up you, me, and everything we see. For every electron, there is a mirror electron. For every quark, a mirror quark. This is not antimatter, which annihilates on contact with ordinary matter. This is something far more ghostly, a complete, symmetric copy of all known physics, forming a parallel world of shadow matter that occupies the exact same space as our own. The only rule, the only bridge between these two realities is gravity. Mirror particles feel the pull of our matter, and our matter feels the pull of theirs because gravity, it seems, does not discriminate. But beyond that, they are utterly invisible to us. Light, the electromagnetic force, the strong and weak nuclear forces, none of these can cross the divide. A mirror planet could pass directly through the Earth, and we would feel only the faintest extra tug of its gravity. A mirror star could be shining brilliantly at the center of our sun, bathing its own invisible planets in light, and we would be completely unaware, seeing only the familiar glow of our own star. This is not a distant bubble universe. It is a co-occupant, a silent roommate sharing our cosmic apartment, walking through our walls as if they were not there. The profound implication is that this mirror sector could be the elusive dark matter that astronomers have been chasing for decades. The mysterious, invisible substance that makes up over 80% of the matter in the universe, holding galaxies together with its gravitational glue, could simply be this vast parallel world of shadow matter. It is not some exotic, unknown particle. It is a perfect copy of everything we know, just operating by its own set of rules in a dimension of reality we cannot access. This idea spins out into astonishing possibilities. If mirror matter obeys the same laws of physics as ordinary matter, just with a separate set of forces, then it too could form atoms, molecules, gas clouds, stars, and planets. Entire mirror galaxies could be intermingled with our own. their spiral arms passing through ours like phantoms. On those mirror planets under mirror suns, the same chemical processes that led to life here could have unfolded there. Mirror DNA, mirror cells, mirror ecosystems could have evolved. There could be mirror oceans, mirror forests, and mirror civilizations, all existing in the same space as our cities and mountains, yet completely unaware of our presence. We are to them the dark matter. The thought is dizzying. A mirror person could be standing in the same spot you are right now, their atoms coexisting with yours in perfect, non-interpenetrating harmony, each of you utterly real and solid in your own layer of reality. You would never bump into them, never see their light, never hear their sounds. The only hint of their entire universe would be the gravitational footprint it leaves on the rotation of galaxies. This transforms dark matter from a cosmic anomaly into a profound philosophical statement about reality. It suggests that what we perceive as the universe is only half the story, a single sheet in a two-ply cosmos. Our reality is not lonely, it is accompanied, haunted by its own perfect reflection. If true, it means we are living in a universe of ghosts where the most substantial things around us are not the stars we see, but the invisible, mirrored worlds we can only feel pulling us silently through the dark. Our silent mirror twin is a ghostly companion, but there exists a far more volatile counterpart born from the very heart of creation. The eighth parallel reality is one of pure, explosive opposition, the antimatter universe. This concept arises from one of the most beautiful and puzzling symmetries in physics. For nearly every fundamental particle we know, there exists an antiparticle, a perfect mirror image with opposite electrical charge. An electron has its antimatter twin, the positron, identical in mass but positively charged. When matter and antimatter meet, they do not pass through each other like shadow matter. They annihilate in a flash of pure energy, a conversion of mass into light so complete that nothing remains. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter. Yet when we look around, our cosmos is made almost entirely of ordinary matter. Where did all the antimatter go? This is one of the greatest unsolved mysteries in science. One compelling answer is that it did not disappear at all. Instead, what if the early universe, in a moment of cosmic sorting, separated the two? Picture the fiery chaos of the Big Bang not as a perfectly mixed soup, but as a roiling sea where bubbles of matter and antimatter began to form. Through some subtle asymmetry in the laws of physics, these domains could have drifted apart as the universe expanded. Most of the matter and antimatter would have annihilated at the boundaries between these vast regions, creating titanic walls of radiation. But within the bubbles themselves, one type would dominate. Our entire observable universe, with its hundreds of billions of galaxies, might simply be one such bubble where matter came out on top. Just beyond the edge of our cosmic horizon, there could be an equally vast domain where antimatter reigns supreme. In that parallel reality, the physics are identical, but the building blocks are inverted. There, anti-hydrogen atoms with positrons orbiting antiprotons fuse in the cores of anti-stars. These antistars would shine with the same light as our Sun, warming antiplanets in orbit. On the surface of an anti-Earth, anti-rocks made of anti-silicon and anti-oxygen would form anti-mountains and anti-oceans. The chemistry of life, if it arose, would be a perfect mirror. An anti-you made of antimatter atoms would think, feel, and wonder about the cosmos, completely identical in every way except for the fundamental substance of its being. The terrifying beauty of this idea lies in its fragility. Should these two cosmic domains ever make contact, the result would be the most energetic event imaginable. If an antimatter asteroid, a mere pebble, drifted into our solar system and struck a matter-based planet, the impact would not be a physical crater. Upon contact, the atoms would annihilate. That pebble, weighing just a few kilograms, would release energy equivalent to a thermonuclear bomb. Now scale that up. the collision of an anti-star with one of our stars would not be a merger or an explosion as we understand it. It would be a conversion, a chain reaction of annihilations propagating at the speed of light, transforming both colossal bodies into an expanding sphere of gamma rays so intense it could sterilize entire galaxies. The boundary between our matter universe and an antimatter neighbor would be a perpetual wall of fire, a cosmic curtain of annihilation radiation marking the end of one reality and the beginning of its opposite. This possibility forces us to see our universe not as the default but as one half of a polarized whole. We are not just lucky to be here, we are lucky to be isolated. Our existence depends on a vast, empty buffer zone, a no-man's land of annihilated radiation that keeps our volatile twin at bay. It suggests that what we call matter might just be a geographical accident, a local preference in a cosmos that, on the grandest scale, remains perfectly balanced between creation and its silent, explosive shadow. The volatile symmetry of an antimatter cosmos reveals a startling truth about our own. The laws that govern it are not just fortunate, they are improbably perfect. This is the puzzle of fine-tuning, a mystery that points directly to our ninth parallel reality, a universe with different physical constants. The forces and numbers that shape our world, like the strength of gravity or the energy of empty space, are not arbitrary. They are dials on a cosmic control panel, and if any one of them were turned even a fraction, the universe as we know it would not exist. Take gravity, the force that sculpts galaxies. If it were just a little stronger, stars would burn through their nuclear fuel at a ferocious rate. Instead of shining for billions of years, giving planets like Earth ample time to cool and life to evolve, stars would blaze and die in mere millions of years. Solar systems would be chaotic, fleeting things with no stable orbits long enough for life to take root. Conversely, if gravity were slightly weaker, matter might never have clumped together to form stars and galaxies in the first place, leaving the cosmos a forever diffuse, dark, and sterile cloud of hydrogen. Or consider the cosmological constant, the energy inherent to the vacuum of space itself, which drives the universe's expansion. In our universe, this number is astonishingly small, yet precisely balanced. If it were even minutely larger, the repulsive force would have been so powerful in the early universe that it would have ripped apart every nascent galaxy before it could form. Space would have expanded at a rate that made the formation of any structure, from stars to atoms, utterly impossible. We would have a vast, empty, accelerating void. Now shift the dial on the nuclear forces. The strong nuclear force binds protons and neutrons together in atomic nuclei. If it were just a few percent weaker, simple hydrogen would be the only stable element. The complex nuclei of carbon and oxygen, the very building blocks of life and planets, could never form. The universe would be a boring sea of hydrogen with no chemistry beyond the simplest reactions. No rocks, no water, no organic molecules. If the strong force were slightly stronger, however, protons could bind together so easily that hydrogen would fuse into heavier elements almost instantly in the early universe, leaving no long-lasting fuel for stars. The cosmic candle would have burned out before it was ever lit. These are not minor adjustments, they are cosmic deal breakers. The fine-tuning extends to dozens of constants and initial conditions, from the mass of the electron to the ratio of matter to radiation in the primordial fireball. The collective precision required for a universe that can eventually host observers like us is so extraordinary that it has led many scientists and philosophers to ask, why this set? Why are the dials set to these exact, life-permitting values? One profound answer, emerging from the multiverse concepts we have already explored, is that they are not set at all. In an infinite inflationary or cyclic multiverse, each bubble universe or new cosmic cycle gets a random roll of the dice for its physical constants. The vast, overwhelming majority of these universes are stillborn or sterile realities where gravity crushes all structure, where expansion shreds reality, or where chemistry is too simple to build anything interesting. Our universe, then, is not a miracle of design, but a statistical inevitability in an infinite ensemble. We could not find ourselves in any of the lifeless universes because there would be no one there to do the finding. We exist, therefore we must be in one of the rare golden tickets, a cosmic habitat where every dial, through sheer luck, landed in the narrow window that allows for galaxies, stars, planets, and life. This perspective transforms the question from, why is our universe so perfectly tuned, to, what does it mean that we live in a universe capable of asking that question? It suggests a cosmos of breathtaking waste, where for every lush, vibrant reality like ours, there are an infinity of silent, empty, or chaotic ones forever unobserved. Our existence is not the point of the cosmos, but a rare and beautiful accident within it. The fine-tuning of our universe suggests a cosmic lottery where most tickets are worthless. But what if one of those losing tickets created a reality not just sterile, but fundamentally inverted? A place where the most basic flow of existence runs in reverse. This is the time-reversed universe, a parallel reality where the arrow of time points backward from our perspective. In our world, time's direction is defined by entropy, the universal tendency toward disorder. An ice cube melts in a warm drink, a shattered glass never reassembles itself, and we remember the past, not the future. These are all consequences of increasing entropy. In a time-reversed universe, entropy would decrease, order would spontaneously arise from chaos. Scrambled eggs would leap from the pan and reassemble into a whole egg in your hand. Splashes of water would gather from the floor and vault back into a glass. The universe would begin in a state of maximum disorder, a kind of thermal chaos, and over what we would perceive as time, it would organize itself into exquisite, intricate structures. This flips causality on its head. In that world, effects would precede their causes. A falling tree would hit the ground before the axe struck it. A light would turn on in a room before someone flipped the switch. The very logic of experience would be alien to us. For conscious beings in such a universe, the flow of personal existence would be equally inverted. Imagine a person being born from the ground, fully formed and elderly, with a lifetime of memories of a future that has not yet happened. They would experience their lives in what we would call reverse. They would start with the wisdom and memories of age, then grow younger, shedding knowledge and experience as their bodies rejuvenate. Their final moments would be as a newborn infant, their consciousness dissolving into a blank slate before returning to the womb. From our vantage point, they are living life backward, but from their perspective, their experience is just as continuous and logical as ours. They would remember tomorrow and anticipate yesterday. The philosophical puzzle this presents is profound. What is consciousness in such a reality? If their brains are wired to remember the future, does that mean their decisions are predetermined? Or does their subjective experience of now simply flow in the opposite direction along the timeline, making free will just as meaningful to them as it feels to us? Their past is our future, a domain of events that, from our perspective, has not yet been determined. This suggests a terrifying intimacy between our universe and a time-reversed twin. Some cosmological models, particularly those examining the conditions at the Big Bang, propose that if the initial state of the cosmos was perfectly symmetric, a time-reversed universe could naturally exist on the other side of the singularity. Picture the Big Bang not as a single starting point, but as a central moment of maximum entropy from which two universes emerge, evolving in opposite temporal directions. We are living in one branch flowing toward greater disorder. The other branch flows toward greater order, its past being our future. In the quantum many-worlds framework, such a universe could simply be another branch, one where the quantum fluctuations that set the arrow of time at the microscopic level aligned in the opposite way. This possibility forces us to confront time not as a fundamental flow, but as an emergent property, a local gradient in the landscape of the multiverse. It asks if our relentless march from birth to death is a universal truth or merely a parochial habit of our particular cosmic neighborhood. If a time-reversed reality exists, then every moment of our future is someone else's fading memory, and our forgotten past is their destiny waiting to be born. The arrow of time may be a local quirk, but the very stage on which reality plays out could be profoundly different elsewhere. Our daily experience is locked into 3 spatial dimensions: length, width, and height. We can move forward and back, left and right, up and down. Every object from a coffee cup to a galaxy exists within this 3-dimensional framework. Yet mathematics and modern physics are clear. There is nothing special about the number 3. A parallel reality could easily possess more. Imagine a universe where space has 4, 5, or even 10 macroscopic dimensions, all extended and accessible, not curled up at a microscopic scale as some theories suggest. In such a place, the most fundamental laws of physics would transform, creating a world utterly alien to our senses. Gravity, for instance, would behave differently. In our 3-dimensional world, gravity weakens with the square of the distance, a law we call inverse square. Double your distance from a planet, and its gravitational pull weakens to 1/4. But in a universe with 4 large spatial dimensions, gravity would obey an inverse cube law. Double your distance and the pull plummets to 1/8. This simple change has catastrophic consequences for cosmic structure. Stars would struggle to hold planets in stable orbits over astronomical distances. Solar systems as we know them might be impossible, with planets either spiraling into their suns or drifting away into the void. Galaxies might never coalesce from swirling gas clouds, leaving the cosmos a diffuse and lonely place. The geometry of everyday objects would defy our intuition. In our 3 dimensions, you can tie a knot in a string because there is enough room to loop and tangle it. In a universe with 4 spatial dimensions, those knots would simply slip apart. There is always an extra direction to maneuver through, making it impossible to create a stable knot in a 1-dimensional line. The very concept of containment changes. In our world, a cell membrane can enclose a cell, and a wall can enclose a room. In 4 dimensions, a 3-dimensional container cannot hold anything in. An object could always slip out through the 4th direction. Life based on sealed compartments like biological cells might be a non-starter. The elegant double helix structure of DNA, which relies on complex twisting and folding in 3-dimensional space, might be geometrically impossible to stabilize, suggesting that the chemistry of life as we understand it could never arise. How would a being native to such a universe perceive its reality? Their senses would be adapted to process information from all accessible dimensions. Where we see a 2-dimensional projection of a 3-dimensional world on our retinas, a 4-dimensional being might perceive 3-dimensional shadows of 4-dimensional objects. An apple to them would not be a simple sphere but a shape whose full form we cannot visualize, a kind of hypersphere. They could look around corners in a way we cannot, seeing the inside of a sealed box without opening it by peering along the 4th spatial direction. Their art, architecture, and technology would be built with this expanded spatial freedom, creating structures and machines of unimaginable complexity that extend in directions we have no words for. Navigating such a world would require a completely different kind of mind. Our brains are exquisitely wired to model 3 spatial dimensions, allowing us to catch a ball, navigate a forest, or build a house. A conscious being in a higher dimensional universe would need a neural architecture capable of modeling 4, 5, or 10 dimensions simultaneously. Their intuition for geometry and physics would be innate, allowing them to manipulate hypervolumes and multi-dimensional vectors as easily as we stack blocks. For them, our 3-dimensional world would seem cripplingly flat, confined, and simple, a prison of limited perspective. This possibility forces a humbling realization. the three dimensions we consider the entire foundation of reality may be nothing more than a local condition, a specific setting in a multiverse where the very number of directions you can move is up for grabs. If life can adapt to such a bizarre spatial landscape, what other unimaginable forms of consciousness might be thriving in the geometries we can only describe with cold equations? The stability of our own universe, with its precise constants and reliable laws, might be a rare island of calm in a sea of cosmic chaos. This brings us to the 12th parallel reality, born from the marriage of eternal inflation and string theory, known as the chaotic inflation landscape. Earlier, we pictured the inflationary multiverse as a frothing sea of bubbles, each a separate universe. The landscape concept adds a breathtaking layer of complexity to this picture. It proposes that the energy field driving inflation is not a single, simple entity, but a vast, mountainous terrain of possibilities with countless valleys, peaks, and plateaus. Each point in this abstract landscape represents a different possible configuration for the laws of physics, a different vacuum state for a universe. As inflation proceeds, different regions of the primordial cosmos can randomly tumble into different valleys in this landscape. When a region settles into a particular valley, inflation ends there, and that specific vacuum state crystallizes into the permanent, fundamental laws for that newborn bubble universe. The energy of the field is released, setting the stage for particles, forces, and dimensions as we know them. But here is the crucial point: which valley a region falls into is essentially a quantum roll of the dice. This means the diversity of bubble universes is not just in their history or matter content, but in their very bedrock. One bubble might land in a valley that yields 4 dimensions of space and our exact strength for electromagnetism. Another might land in a valley that produces a universe with 10 extended dimensions and a gravity 100 times stronger. Another might yield a cosmos where the nuclear forces are too weak to form atoms heavier than helium, forever limiting chemistry to the simplest elements. The landscape, according to some calculations in string theory, could contain an astronomically large number of possible configurations, perhaps 10 to the power of 500 or more. This is not just a large number, it is a number that dwarfs the count of all atoms in our observable universe. It represents an unfathomable variety of possible physical realities. This is where the anthropic principle enters, not as an explanation but as a stark filter. In this near-infinite ensemble of universes, the overwhelming majority will be stillborn or sterile. They might collapse instantly into black holes, expand so rapidly that no structures ever form, or possess laws of physics that cannot support any complexity, let alone conscious observers. We, quite obviously, do not find ourselves in those universes. We can only exist in one of the exceedingly rare bubbles where the random tumble into the landscape produced a Goldilocks set of laws, a vacuum state that allows for stars, planets, stable atoms, and the long, slow processes of cosmic and biological evolution. Our universe is not fine-tuned by design, it is self-selected by the fact of our presence. We are living in a cosmic lottery winner, but the prize is simply the chance to look around and wonder at our own improbable existence. The landscape makes the multiverse not just vast, but almost exhaustively creative, containing every physically possible universe that mathematics allows, from the lush and life-giving to the utterly barren and bizarre. It suggests that for every universe like ours, there are countless others where the very concept of a planet, or even a molecule, is a physical impossibility. The chaotic landscape of inflation offers a cosmic lottery of physical laws, but there exists a far more intimate and violent engine of creation, hidden in the darkest objects in our own sky. At the heart of a black hole lies a point of infinite density, a singularity where our known laws of physics break down completely. Some physicists have dared to ask a radical question: what if that point of breakdown is not an end but a new beginning? This leads us to the 13th parallel reality, the daughter universe, born from the terrifying womb of a black hole. The idea, known as black hole cosmology, suggests that the crushing singularity inside a black hole does not erase everything that falls into it. Instead, it could be the spark for an entirely new Big Bang, birthing a separate, self-contained spacetime, a child universe branching off from our own. In this model, our entire cosmos might itself be the interior of a black hole formed in a larger parent universe, creating a cosmic matryoshka doll of realities, each nested within the other. The process is as elegant as it is extreme. As matter and energy cross the event horizon of a black hole, they are accelerated and compressed to unimaginable extremes. According to some theoretical models, this could trigger a quantum bounce, a rebound from infinite density that initiates a new phase of explosive expansion. From the outside, in our universe, the black hole is a dark, nearly featureless prison from which nothing escapes. But from the inside, for the matter that has crossed over, it is the first blinding moment of a new creation, a universe with its own dimensions, its own flow of time, and its own future. The most profound implication of this idea concerns information. One of the great puzzles in physics is the black hole information paradox. What happens to the information about the properties of matter that falls in? If it is truly lost, it violates a fundamental tenet of quantum mechanics. The daughter universe concept offers a breathtaking solution. The information is not destroyed, it is translated. The quantum information of every star, planet, or astronaut that ever fell into the black hole could be imprinted onto the initial conditions of the new universe's Big Bang. In a sense, the physics of the daughter universe, the strengths of its forces, the number of its dimensions, the very patterns of its cosmic microwave background, could be a scrambled, reborn echo of everything that was consumed by the parent black hole. Our universe's constants might be the unique signature of whatever met its end in a black hole in a higher reality. This creates a fractal tree of existence, an endless lineage of universes giving birth to new ones through their most destructive phenomena. Each black hole in our cosmos could be a portal to a separate, fledgling reality, each with its own destiny. Some daughter universes might be stillborn, collapsing back in on themselves instantly. Others might expand into vast, rich cosmos like our own, eventually spawning their own black holes, which then give rise to their own daughter universes in turn. We could be living in just one branch on an infinite, growing tree of cosmoses, each connected to its parent by a one-way tunnel through space-time. This transforms black holes from ultimate endpoints into cosmic seeds. The terrifying engines of gravitational oblivion become creators. It suggests that death on the grandest scale is not an annihilation, but a metamorphosis, a recycling of reality into new forms we can never visit or communicate with. If this speculative vision is true, then somewhere, in the heart of the supermassive black hole at the center of our Milky Way, an entire cosmos is being born from the ashes of swallowed stars, a universe whose fundamental nature is a direct inheritance from the lost information of our own. Black holes may birth new realities, but the laws governing those realities are not guaranteed. The weak nuclear force is a ghostly presence in our daily lives, yet it is the quiet architect of our very existence. This force governs radioactive decay, the process where unstable atomic nuclei shed particles to become more stable. It is the reason some elements are radioactive, and crucially, it plays a starring role in the nuclear furnaces of stars. Without it, the universe would be a profoundly different and likely much simpler place. In a cosmos lacking the weak force, the first and most dramatic change would occur in the hearts of stars. In our Sun and similar stars, hydrogen fuses into helium through a multi-step process called the proton-proton chain. A key step in that chain relies on the weak force to transform a proton into a neutron, allowing the fusion process to proceed and release the energy that makes stars shine. In a weakless universe, this pathway is blocked. Stars would need to rely on far less efficient methods to generate energy if they could ignite at all. The brilliant beacons that light our cosmos might be dim, fleeting, or never form in the first place, leaving the universe a darker, colder expanse. But the consequences run even deeper into the very elements that make up our world. The weak force is essential for a cosmic alchemy called the S process, or slow neutron capture process. This occurs in the late stages of older giant stars. Free neutrons produced by other nuclear reactions are slowly captured by atomic nuclei. The weak force then allows a neutron within that nucleus to decay into a proton, effectively transforming the element into the next one on the periodic table. This slow, stepwise process is responsible for creating roughly half of all elements heavier than iron, including vital ones like copper, silver, and gold. In a universe without the weak force, this elegant production line grinds to a halt. The creation of these heavier elements would be severely stunted, if not impossible. The cosmic abundance would be skewed dramatically toward the lightest elements, hydrogen, helium, and perhaps a trace of lithium and beryllium. The rich chemistry of our world, built on carbon, oxygen, nitrogen, and iron, would simply not exist. There would be no carbon for organic molecules, no iron for planetary cores, no silicon for rocky worlds. Planets themselves might be rare or impossible, reduced to cold, gaseous balls of primordial hydrogen and helium. Could any form of complex chemistry or even life arise in such an elemental desert? The prospects appear bleak. Life as we understand it requires a diverse palette of atoms to build complex, self-replicating structures. In a weakless universe, the periodic table would be a short, sad list. Chemical bonding would be limited to the few simple interactions possible between the lightest gases. There would be no solvents like water, no scaffolding like DNA, no catalysts like enzymes. The universe would be stuck in a permanent state of cosmic infancy, forever lacking the building blocks for complexity. Stars, if they managed to form, would burn differently and die, leaving behind inert husks of helium, unable to enrich the cosmos with the ashes of heavier elements. It would be a silent, stagnant, and profoundly simple reality. This stark possibility highlights a humbling truth about our own existence. We are not just products of a universe with gravity and light. We are children of a specific, subtle force that allows stars to shine and atoms to transform. The weak nuclear force, so often overlooked, is not a minor detail in the cosmic rulebook. It is a fundamental clause that permits the story of complexity, and perhaps life itself, to be written at all. Its absence would erase not just our history, but the very possibility of a history worth telling. The absence of the weak force would render a cosmos silent and simple, but what if the opposite were true? What if the universe is not just complex, but fundamentally awake? This leads us to a profoundly different kind of parallel reality, one not defined by altered physics, but by an intrinsic quality of existence itself. We have arrived at the conscious universe, a vision rooted in the ancient philosophy of panpsychism. In this view, consciousness is not an accidental byproduct of complex brains, like steam emerging from a boiling kettle. Instead, it is a basic, fundamental property of the universe, as intrinsic to reality as mass or electrical charge. Just as electrons possess charge and mass, they might also possess an infinitesimal degree of raw, elemental experience. In our world, this ubiquitous proto-consciousness only coalesces into the rich inner life we recognize in complex systems like the human brain. But in a panpsychist multiverse, each bubble or branch could have a different foundational relationship with this property. Imagine a universe where consciousness is not a rare flame flickering in biological skulls, but the very fabric of spacetime. In such a reality, the cosmos itself could be a single, vast, dreaming entity. Galaxies might not be mere collections of stars, but thoughts within a cosmic mind, swirling patterns of cognition in a being so immense we are but fleeting neural impulses within it. The birth of a star would be a moment of inspiration, the death of a black hole a profound forgetting. The laws of physics in this universe would not be cold equations, but the ingrained habits of a deity's dream, the stable patterns of its ongoing meditation. For life evolving on a planet within such a cosmos, existence would be fundamentally participatory. Your thoughts might not be entirely your own, but localized eddies in a universal stream of awareness. Intuition and creativity could be moments of direct resonance with the overarching mind, a tuning into the background hum of a sentient reality. Conversely, imagine a universe where the gradient is reversed and consciousness is so diluted or scattered that it never coalesces into what we would recognize as a mind. Here, every rock, every photon of light, every empty patch of space might have a faint, isolated point of view, a universe of a trillion lonely whispers, each experiencing a single, eternal note of existence without connection or context. This is not life, but a cosmos where experience is atomized, a dust of sensation without memory or meaning. A panpsychist multiverse forces us to redefine intelligence and life entirely. In a branch where inanimate objects have rich, coherent experiences, a mountain could possess a geological patience, a slow, grinding awareness of erosion and uplift over eons. A river might have a fluid, flowing consciousness of its journey to the sea. In such a place, communication would not be through sound or sight, but through a deeper, more direct resonance of experience. To build a shelter, you might need to negotiate with the consciousness of the wood and stone, persuading them to hold a new form. Technology would be less about engineering and more about diplomacy with the aware materials of the world. This radically alters the cosmic search for other minds. In our universe, we scan the stars for radio signals or techno-signatures, looking for mirrors of our own technological intelligence. In a panpsychist multiverse, the most advanced civilization might not use radio at all. It might be a forest whose root systems have achieved a collective, planet-spanning awareness, communicating through chemical and electrical signals in the soil, thinking thoughts as slow and deep as continental drift. Or it might be the magnetic field of a star, a vast, swirling sentience that perceives the universe through lines of force and pulses of radiation utterly alien to us. If consciousness is fundamental, then life is not a prerequisite for having an inner world. It asks the most unsettling question of all: is our universe conscious, and are we simply the means by which it has begun to know itself? Our journey through the multiverse has explored worlds of altered physics and fundamental consciousness, but there is a possibility that strikes at the very nature of reality itself. The 16th parallel universe is not built from different laws, but from a profound illusion. This is the holographic universe, a reality where everything you see, touch, and experience is a magnificent projection, a three-dimensional movie playing on a two-dimensional screen. The idea emerges from a startling discovery about black holes. When matter falls into a black hole, it seems to vanish, taking its information with it. This creates a paradox because quantum mechanics states information can never be truly destroyed. To resolve this, physicists found that all the information describing the matter that fell in could be perfectly encoded on the black hole's event horizon, its two-dimensional boundary surface. The three-dimensional interior, with all its complexity, is somehow represented entirely on its two-dimensional surface like a hologram. Extend this principle to the cosmos itself. The holographic principle suggests that all the information contained within any volume of space, every star, every planet, every human thought, is not stored within that volume. Instead, it is painted pixel by pixel on the distant boundary that encloses it. For our entire observable universe, this means the three-dimensional reality we inhabit, with its rich depth and solidity, could be a projection from a vast, cold, two-dimensional shell at the very edge of everything. We are not living inside the cosmos, we are living inside its shadow. Our perception of a three-dimensional world is a kind of cosmic sleight of hand, an emergent property of information processing on a flat surface far beyond the farthest galaxy. The solidity of the ground beneath your feet, the warmth of sunlight on your skin, the vast distances between stars, all of it is a translation, a rendering of data from a fundamentally simpler, lower-dimensional reality. Now, stretch this concept across the multiverse. If our universe is a three-dimensional projection from a two-dimensional boundary, what other projections are possible? Imagine a parallel reality that is a four-dimensional projection from a three-dimensional boundary. For inhabitants of that cosmos, their world would feel hyper-solid, with a depth and spatial complexity we cannot fathom, yet it would be just as illusory, a shadow cast from a container with one fewer dimension. Conversely, picture a universe that is our two-dimensional projection, but from a one-dimensional boundary, a single, impossibly long line where all information is stored. The beings in that universe would experience a flat, planar world, completely convinced of its tangibility, never knowing they are the animated output of a cosmic barcode. This transforms the nature of existence in these parallel worlds. In a holographic reality, the laws of physics are not fundamental dictates but derived rules, the user interface of a deeper computational process. A glitch in the projection could manifest as a temporary suspension of gravity in a local area, or a region where time appears to stutter and repeat. For the simulated inhabitants, these would be unexplainable miracles or terrifying anomalies. Their scientists would strive to find laws to explain these events, never guessing they are debugging artifacts from a higher dimensional code. The search for a unified theory in such a universe becomes the search for the compression algorithm, the set of rules that translates the boundary data into the rich interior experience. This idea offers a bizarre answer to the fine-tuning puzzle. Perhaps the physical constants of our universe are not randomly selected, but are the most efficient or stable settings for translating two-dimensional data into a consistent three-dimensional experience. A different holographic universe with a different translation algorithm would produce a completely different set of apparent laws for its inhabitants. One might have a speed of light that fluctuates or a gravity that grows stronger with distance, simply because that is how its particular projection math works. The most profound implication is for the nature of consciousness within a holographic cosmos. If your mind is part of the projection, then your thoughts, memories, and sense of self are also encoded on that distant boundary. Your stream of consciousness is the real-time rendering of your informational data. This blurs the line between the simulated universe we discussed earlier and the holographic one. In one, the simulation is run on a computer in a higher reality. In the holographic model, the simulation is the intrinsic nature of spacetime itself. A self-contained illusion with no outside programmer needed. Reality is its own projection. It suggests we are not just in a universe, we are an image of a universe, a story that a boundary is telling itself. If that is true, what happens when the projection reaches its edge, or when the information on the boundary finally reaches maximum density? Does the movie simply end, or does it begin to replay? The holographic universe suggests our reality is a shimmering projection, but every projection must eventually fade to black. There exists a parallel reality that is the ultimate, inescapable end of that process, a cosmos not of creation, but of perfect, irreversible conclusion. This is the universe of eternal static, the final chapter written by the second law of thermodynamics. In our universe, entropy, the measure of disorder, always increases. Stars burn out, structures decay, and energy spreads thin. Given enough time, an almost incomprehensible amount of time, this leads to a single, inevitable destination: heat death. Now picture a parallel reality, perhaps a distant bubble in the inflationary foam, or the far future of a cosmos like ours that has already arrived. This is a universe that has reached maximum entropy. Every ounce of usable energy has been spent. Every temperature gradient has been smoothed away. The entire cosmos exists at a uniform, frigid temperature, just a whisper above absolute zero. In this state, nothing can ever happen again. There are no stars, for nuclear fusion requires a concentration of matter and energy that no longer exists. There are no planets, as any solid bodies would have long since evaporated through a process called quantum tunneling, their particles dissipating into the void. There are not even any atoms in a stable form, as protons themselves may have decayed after trillions upon trillions of years. The universe is a vast, dark, and perfectly uniform sea of incredibly low-energy photons and subatomic particles drifting infinitely far apart. Time still exists, but it has lost all meaning. With no processes, no change, and no events to mark its passage, time becomes an empty coordinate, a dimension without a story. This is not a place of cold, silent beauty. It is a place of absolute nullity. Contrast this with our own vibrant, chaotic, and evolving cosmos. Right now, we live in the golden age of structure. Gravity has sculpted magnificent galaxies. Stars forge heavy elements in their cores. On at least one planet, chemical gradients drive the complex machinery of life. We are in the brief, bright middle of the story, nestled between the explosive beginning of the Big Bang and the unimaginably long twilight of heat-death. The universe of eternal static shows us the chilling counterpoint to our existence. It is a reality where the arrow of time has finally, completely lost its target. For any conscious being unfortunate enough to witness the approach of this state, it would be a slow-motion apocalypse of fading possibilities. First, the stars would wink out, leaving galaxies as ghostly collections of dead stellar remnants. Then, over epochs so vast they dwarf the current age of the universe, even those remnants, black holes, would evaporate via Hawking radiation, their final pops of energy dissipating into the expanding dark. Finally, with no engines of change left, reality would settle into its final equilibrium state. This serves as the ultimate parallel reality, not in space but in time. It is the future that may await every universe that does not collapse or bounce, a solemn reminder that all stories, even cosmic ones, may have an end. It asks a haunting question of our own vibrant moment. If this static eternity is the inevitable destination, does that make the fleeting dance of galaxies and life more precious or more tragically meaningless? The answer may depend on which parallel version of yourself you ask. Gravity is not the only sculptor in the cosmos. A parallel reality exists where the true architect of the universe is not the quiet pull of mass, but the fierce, dynamic crackle of electricity. This is the plasma universe, a vision from an alternative cosmology where electromagnetic forces reign supreme over gravity. In this cosmos, space is not a near-perfect vacuum dotted with isolated islands of matter. It is a vibrant, conducting medium, a sea of ionized gas called plasma, threaded by vast, flowing currents and immense magnetic fields. Here, the formation of stars and galaxies is not a slow, gravitational collapse, but a sudden, brilliant flash of cosmic-scale lightning. Picture the interstellar medium not as a dark, silent void, but as a shimmering, luminous network. Gigantic filaments of plasma, light years across, crisscross the cosmos like the veins of a celestial body. These filaments carry electric currents of unimaginable power, flowing through the conductive plasma of space. Where these currents twist and pinch together, they can ignite the birth of a star in a process called a Z-pinch. Instead of a cloud of gas slowly condensing under its own weight, a star in this universe would light up suddenly, like a brilliant bead of plasma on a cosmic wire, its energy fed by the galactic circuit it is part of. The familiar shapes of spiral galaxies are not gravitationally bound whirlpools. but the visible imprint of these massive, rotating Birkeland currents, twin helical flows of electricity that spiral through the depths of space, lighting up with stellar nurseries along their path. For life evolving on a planet within such a universe, the sky would be a constant, breathtaking spectacle. The aurora would not be a rare polar event, but a permanent, global feature, painting the heavens in shimmering curtains of light as the planet moves through the galactic plasma currents. The night sky might be lit by permanent, gentle nebulous glows and sudden, terrifying arcs of interplanetary lightning. Storms on such a world would be apocalyptic, fueled not just by weather, but by direct connections to the electrical activity of its star and the wider galaxy. The very geology of planets would be shaped by electrical scarring, with mountain ranges possibly forming from titanic plasma discharges that once sculpted the crust like a cosmic welder. Evolution itself would be forced to adapt to this crackling environment. Life forms might develop sophisticated electromagnetic senses, able to perceive the ebb and flow of galactic currents directly, navigating by the magnetic fields that structure their world. Their technology would likely harness plasma and electromagnetic forces long before understanding gravity. Flight might be achieved through electromagnetic levitation rather than aerodynamics. Communication could occur through modulated plasma pulses sent through the atmosphere itself. For these beings, the idea of a universe dominated by a weak, invisible force like gravity would seem as absurd as a universe without light. Their entire physics, their mythology, and their understanding of their place in the cosmos would be built on the primacy of the electric force. This parallel reality challenges our most fundamental assumptions, asking if the quiet, dark cosmos we see is the whole story, or merely a disconnected snapshot of a universe that is fundamentally alive, connected, and electrically brilliant. Our most trusted cosmic messenger carries a hidden secret. The speed of light is not just a number in a physics book, it is the universe's ultimate speed limit, the constant that stitches together space and time into the single fabric of relativity. But what if that constant was not constant at all? In a parallel reality, the speed of light is a variable, a number that can change from place to place or ebb and flow across the ages. This single alteration would not just tweak the laws of physics, it would shatter the foundational logic of reality as we know it. In our universe, the speed of light is the same for every observer, no matter how fast they are moving. This simple, bizarre fact is what leads to time dilation and length contraction, the pillars of Einstein's theory. It is why nothing can travel faster than light, for to do so would be to travel backward in time, violating causality. But in a universe where light's speed can vary, these sacred rules crumble. Picture a region of space where light crawls. In this cosmic tar pit, the speed of light might be reduced to a mere walking pace. The consequences are immediate and terrifying, because the speed of light defines the maximum rate at which information can travel. It also defines the flow of causality itself. In this slow light zone, cause and effect would grind to a near halt. A person standing at one end of a room could wave their hand, and an observer at the other end might not see it for minutes or even hours. By the time they reacted, the cause would be ancient history. Communication becomes impossible, and the very notion of now dissolves into a meaningless fog of delayed signals. Time itself, from an outside perspective, would appear almost frozen within this region. Now, imagine the opposite extreme, a domain where light travels at speeds millions of times faster than in our cosmos. Here, information is nearly instantaneous. You could see the surface of a planet on the far side of the galaxy as it is happening, with no delay. But this superluminal speed demolishes the sequence of events. An effect could be seen before its cause has even occurred from a distant vantage point. In such a place, the universe's timeline would be a tangled knot. You could potentially receive a message warning you of a disaster before the event that triggered the warning had taken place, opening the door to paradoxes that make time travel seem simple. The structure of spacetime in such a universe would be unrecognizable. Einstein's elegant equations of general relativity, which depend on a constant speed of light, would warp into something chaotic. Gravity might behave in wildly unpredictable ways, with black holes having different properties or perhaps not forming at all. The cosmic horizon, the limit of what we can see, would be a shifting, phantom boundary. In some eras of this universe's history, when light raced faster, the observable cosmos would be vast, connecting distant regions that are forever separate in our own. In other eras, when light slowed, the universe would effectively fragment into isolated pockets, each trapped within its own tiny, causally disconnected bubble. For any form of life trying to make sense of this reality, science would be a nightmare. Experiments would yield different results depending on where or when they were conducted. The fundamental constants of nature would be inconstant, making the search for universal laws a futile pursuit. Astronomy would be an exercise in deciphering a scrambled signal, as light from distant stars arrived with speeds that betrayed not just distance, but the local conditions of the space it traveled through. A blue shift might not mean a star is moving toward you, but that its light has just passed through a region where light speed was temporarily increased. This universe challenges our deepest assumption that the rules are the same everywhere. It suggests a cosmos that is not a uniform stage, but a fractured and capricious realm where the very tools we use to understand reality, light and time, are fundamentally unreliable. If the speed of light can change, then what, in the end, is truly constant? The universe we know builds life from stardust, a rare miracle in a cosmos of rock and fire. But there exists a parallel reality where this distinction never formed. A cosmos where the boundary between the living and the non-living is a meaningless concept. This is the organic universe, a realm built not from inert atoms, but from the very essence of life itself. Here, the laws of physics are perfectly tuned not for nuclear fusion or gravitational collapse, but for the spontaneous, exuberant blossoming of organic chemistry. Carbon is not just an element, it is the fundamental architect of reality. Picture the void of space not as a cold vacuum, but as a kind of nurturing ether, a primordial soup charged with the potential for complex bonds. In this rich medium, stars are not blazing balls of hydrogen plasma. They are colossal, slowly metabolizing structures, vast networks of carbon chains and aromatic rings held together by cosmic-scale molecular forces. They do not burn, they respire, drawing energy from the chemical gradients of the galactic medium, glowing with a deep biochemical luminescence. Their light is not the harsh glare of fusion, but the warm, varied glow of a trillion organic reactions, shifting in color like the bioluminescence of a planet-wide ocean. Planets in this universe are not spheres of rock and metal. They are more like giant, intricate cells or fungal fruiting bodies. Their surfaces a continuous tapestry of self-organizing chemistry. Mountains might be vast polymers stretching toward a chemical sun, and oceans could be solvents rich with amino acids and nucleotides, constantly churning with probiotic activity. The very ground you walk on would be alive in a sense, not with creatures, but with a slow geological metabolism, exchanging compounds with the atmosphere in a planetary-scale circulatory system. In such an environment, what we call life does not arise. It is the default state of matter. Self-replicating, complex molecular systems would form as naturally as crystals do in our world, emerging from the etheric medium like condensation on a cosmic window. Evolution would not be a biological process confined to planets, but a cosmological one. Galaxies themselves could be seen as evolving superorganisms, their spiral arms exchanging complex organic compounds, seeding star-forming regions with new molecular information. A nebula would not be a nursery for future stars, but a kind of galactic placenta, a region of intense biochemical synthesis birthing new organic stellar systems. For a consciousness emerging in this universe, the experience of reality would be utterly alien. Their science would not begin with physics and chemistry as separate disciplines, but with a unified theory of organic cosmology. They might perceive the universe as a single, breathing entity, and themselves as conscious nodes within its vast living network. The idea of a dead, inert rock would be as philosophically troubling to them as the concept of a universe without meaning is to us. Their exploration would not be a search for habitable zones because the entire cosmos is habitable. It would be a quest to understand different states of cosmic health, different modes of galactic consciousness, or the life cycle of organic stars. This reality presents the ultimate answer to the fine-tuning problem. In our cosmos, the constants seem improbably set to allow for a tiny oasis of life. In the organic universe, the constants are set to mandate life. Existence is not a neutral stage upon which biology briefly dances. It is the dance itself, a perpetual, spontaneous expression of complex, self-organizing chemistry from the quantum scale to the galactic. It forces us to ask a humbling question. Is our universe, with its separation of life and non-life, the special one? Or is it the sterile, mechanistic outlier in a multiverse that is overwhelmingly, vibrantly alive? The very fabric of reality might be a frozen geometry, a perfect lattice extending to infinity. This is the crystalline universe, a cosmos where space itself is not a smooth, continuous stage, but a rigid, discrete crystal. At the smallest conceivable scale, existence is a grid of fixed points like the atoms in a diamond, with empty voids in between. In this reality, the particles we know, electrons, quarks, photons, are not tiny dots but vibrations or disturbances within this cosmic lattice, like musical notes played on a crystal harp. When an electron moves from one point to another, it is not traveling through empty space. Instead, it is a propagating flaw, a defect in the crystal structure that hops from one lattice site to the next, much like a crack spreading through ice. This fundamental difference rewrites the rules of motion and perception. Just as sound has a maximum speed in any material, you cannot shout through steel faster than its natural limit, so too does light and information in this crystalline cosmos. The speed of light is not a fundamental constant of empty vacuum, but the maximum propagation speed of a disturbance through the lattice, analogous to the speed of sound in a solid. This creates a universal speed limit, but one born from structure, not relativity. More strikingly, a crystal has inherent symmetry. A diamond looks different when viewed along certain axes compared to others. In a crystalline universe, this means space itself has preferred directions. The laws of physics would not be perfectly symmetric in all directions as we assume in our cosmos. Light might travel slightly faster along one crystal axis than another, causing distant stars to appear warped in specific, predictable patterns. The cosmic microwave background, the afterglow of creation, would not be a uniform smear of radiation. Instead, it would carry the imprint of the underlying crystal structure, like holding a stained glass window up to the sky and seeing the lead lines etched across the heavens. For beings evolving in such a universe, their entire science would begin with crystallography, not gravity. Their intuition for geometry would be innate, and the concept of perfectly smooth, empty space would be an abstract philosophical notion, not an observable truth. Their telescopes might be designed to detect the subtle directional biases in starlight, mapping the grand architecture of the crystal that contains them. Even time itself could be a discrete property, ticking forward in quantum jumps as the lattice vibrates, suggesting that the continuous flow we experience is merely an illusion of scale. This universe presents a profound alternative. What if the emptiness we take for granted is an intricate, solid geometry, and we are merely ripples in its frozen perfection? Our crystalline cosmos suggests reality might be a frozen, geometric grid. But what if that grid is not a passive structure, but an active processor, and reality itself is the output of a calculation? The 22nd parallel universe is one of pure information. Here, matter and energy are not the fundamental substances. They are emergent illusions, side effects of something far more basic: computation. In this reality, the cosmos is not a collection of things, but a vast running program. It could be an unimaginably complex cellular automaton, like a cosmic game of life, where simple rules applied to a grid of cells give rise to intricate, evolving patterns. Or it could be a quantum computer of cosmic scale, processing probabilities in a superposition of states. In either case, the stars, planets, and even the space between them are not physical objects in the traditional sense. They are stable, self-perpetuating patterns of data within the grand computation. A galaxy is not a gravitationally bound swarm of stars, but a particularly elegant and persistent algorithm running in the cosmic machine. The laws of physics we consider immutable are not discovered, they are the source code. Gravity is not a force, but a rule governing how information patterns interact over the grid. The speed of light is the maximum processing speed for information transfer across the system. A black hole might be a region where the computation becomes so dense or self-referential that it forms a logical singularity, a point where the program's rules break down or enter an infinite loop. For beings that arise within such a universe, existence is a profound paradox. You are not a biological entity made of atoms. You are a self-aware, coherent pattern of information, a ghost in the cosmic machine. Your body, as you perceive it, is the user interface your consciousness has developed to navigate the data stream. Your senses are not gathering information from an external world, but interpreting specific data outputs from the universal processor. When you touch a rock, you are not feeling solid matter, but interacting with a highly stable, low-entropy information pattern that the rules of the simulation consistently render as solid. Thought itself is simply computation, a sub-process within the greater program. This reframes every mystery. The origin of the universe is not a big bang, but the moment the program was initialized, perhaps with a single bit flipping from 0 to 1. The fine-tuning of physical constants is simply the selection of a particularly fruitful and complex rule set from a library of possible programs. The arrow of time is the direction of computational irreversibility, the fact that the processor cannot easily undo its last trillion steps. In such a cosmos, exploration and science take on a new meaning. Astronomers would not be studying distant light, but analyzing the underlying data structures and algorithms that generate the appearance of light. A physicist might be a kind of cosmic programmer, reverse engineering the source code by observing its outputs. The ultimate goal of knowledge is not to understand forces, but to read the program. This leads to a haunting possibility. If the universe is a computation, it must be running on something. Is there a substrate, a hardware, outside the simulation? Or is the idea of a substrate itself an illusion generated by the program? The beings within might never be able to answer that, forever trapped in the beautiful, logical prison of their own existence, wondering if the programmer is still watching, or if the machine is simply running on its own into an infinite and lonely future. A perfect symmetry lies broken in our cosmos. Every magnet you have ever held, from a simple fridge magnet to the entire planet Earth, comes with an inseparable pair, a north and a south pole. Snap a bar magnet in half and you do not get isolated poles. You create two new, smaller magnets, each with its own north and south. This seems like a fundamental rule, but our best theories of the early universe suggest it should not be this way. They predict the existence of magnetic monopoles, particles that are pure north or pure south magnetic charges, as fundamental as a single positive or negative electric charge. For reasons unknown, our universe appears to have almost none, but in a parallel reality, the story unfolded differently. This is the magnetic monopole universe, a cosmos where these solitary poles are as common as electrons, and their presence rewrites the laws of physics from the ground up. Here, electricity and magnetism achieve a profound and beautiful symmetry. In our world, these two forces are described by Maxwell's equations, but they are not perfectly mirrored. Electric charges exist in isolation, but magnetic poles do not. In the monopole universe, that asymmetry vanishes. The equations become perfectly balanced, with magnetic charges standing alongside electric ones as equal partners. This symmetry would be evident in every corner of reality. Just as positive and negative electric charges attract and repel, so too would north and south monopoles. You could have a cloud of pure north magnetic charge or a stream of south monopoles flowing like an electric current, creating what physicists call a magnetic current. This new fundamental ingredient would cook up forms of matter and energy we can scarcely imagine. Atoms could have not just an electric structure with electrons orbiting a nucleus, but a magnetic one as well. Imagine magnetically charged atoms where monopoles orbit a core, creating substances with bizarre and powerful magnetic properties from the inside out. Stars might form not just from gravitational collapse, but from the gathering of like magnetic charges, their fusion processes influenced by intense, inherent magnetic fields born from their very substance. The emptiness of space would be threaded not just with the faint electromagnetic fields we know, but with a vibrant background of magnetic charge potential, a new frontier for energy. For a technological civilization evolving in such a cosmos, the harnessing of monopoles would be as fundamental as our use of electricity. Their power grids might not rely on moving electrons through wires. Instead, they could channel magnetic currents through specially designed conduits, potentially with far less energy loss than our electrical systems suffer. Their engines for spacecraft would not need bulky fuel tanks. By creating a gradient of magnetic charge, a pure north pole at the front of a ship and a south at the rear, they could essentially fall through the cosmic magnetic field, achieving propulsion by pushing against the fabric of space itself in a way that resembles science fiction's dream of a reactionless drive. Their entire material science would be built upon magnetic chemistry. They could design materials that are supermagnetic at room temperature, or create locks and structures held together by pure magnetic bonds that are far stronger than any chemical glue. Communication might not use radio waves, but modulated beams of coherent monopoles, allowing for signals that pass effortlessly through planets or stars. For them, our struggle to find even one of these particles would seem as strange as a universe without electrons. Their reality is one of complete electromagnetic harmony, a universe that sings with a fuller, more symmetric set of notes than our own. It asks us a quiet question about our own lopsided cosmos. What cosmic event silenced the magnetic solo, leaving only the duet? Silence is not the default state of the cosmos, only a limitation of our perception. There exists a parallel reality where the universe is not a dark, visual expanse, but a vibrant, resonant chamber. This is the acoustic universe, a sonocentric cosmos where sound is the fundamental fabric, and reality itself behaves like a cosmic superfluid, a perfect medium for vibration. In this realm, information does not travel on silent beams of light, but on waves of rich, complex sound. The vacuum of space is not empty, it is a plenum, a subtle, frictionless fluid that carries every vibration perfectly without loss. Here, the most distant events are not seen but heard. A supernova is not a flash, but a catastrophic chord, a booming dissonance that ripples across galactic distances, telling stories of mass and collapse through its timbre and decay. Stars themselves are not silent fusion reactors. They are sonic stars, colossal spheres of oscillating superfluid that emit not simple light, but intricate, evolving harmonies. Each star has its own acoustic signature, a deep, resonant bass for a red giant, a brilliant, piercing treble for a hot blue star. Constellations are not pictures but symphonies, their combined frequencies creating celestial melodies that shift as the planets within their systems move, a grand orchestral dance conducted by gravity. For civilizations that evolve in this resonant reality, perception is built on vibration. They might not have eyes, but exquisite membranes or internal structures tuned to a vast spectrum of sonic frequencies. They would see their world by emitting clicks and listening to the returning echoes, building a three-dimensional soundscape of breathtaking detail. They could hear the texture of a mountain range from miles away, discern the internal structure of a rock by its resonant ring, and perceive the emotional state of another being by the subtle harmonics in its voice. Their art and communication would be based on sound in ways we can barely conceive. Architecture would be designed for perfect acoustics, with cities acting as giant musical instruments, their very structures humming with the activity of life within. Their music would not be mere entertainment, but a direct language of mathematics and physics, a way to encode complex data, history, and emotion into layered vibrations. They might communicate across continents using focused beams of low-frequency sound that travel through the planetary crust, or send messages between stars by modulating the resonant frequencies of the interstellar superfluid itself. The most profound sonic artifact, however, would be the echo of creation itself. Just as our universe has a cosmic microwave background, a fossilized glow from the Big Bang, the acoustic universe would have a cosmic acoustic background. It would be a faint, omnidirectional hum, a fundamental tone upon which all other sounds are built, the enduring vibrational signature of the universe's first moment. For its inhabitants, this eternal symphony is not just noise, it is the foundational note of reality, a constant reminder of their cosmic origin, and the harmonic framework against which all other phenomena are measured. In such a world, to understand the cosmos is not to seek the theory of everything, but to listen for the ultimate chord, the one vibration that perfectly explains the magnificent, resonant song of existence. The symphony of a resonant cosmos fades into a profound, almost unsettling silence. Among the infinite possibilities we have explored, from conscious universes to crystalline grids, there exists a final, deeply personal frontier. It is the universe next door, a reality so similar to our own that the difference is not measured in altered laws or alien physics, but in the placement of a single, stray atom. In this ultimate parallel world, everything is virtually identical. The same stars burn in the same constellations, the same history unfolded with the same wars, discoveries, and works of art. Your life up until this very moment is a perfect mirror. You have the same memories, the same relationships, the same scars and triumphs. The divergence point is so trivial it borders on the absurd. Perhaps in that universe you turned left instead of right on your way to work this morning, missing a green light by half a second. Maybe you chose a different brand of cereal from the supermarket shelf, a decision of no consequence. Or on a scale even smaller, a single photon of light reflected off a window at a slightly different angle, or one atom in the rings of Saturn is in a different position in its orbit. That is the only change. From that infinitesimal fork in the road, two nearly perfect copies of reality begin their slow, inexorable drift apart. The philosophical weight of this idea is immense. It suggests that for every choice you make, no matter how insignificant, there is another version of you who made the opposite choice. There is a you who is, at this second, taking a sip of coffee instead of reading this sentence. A you who married a different person, a you who moved to a different city, a you who hesitated for one extra moment before speaking a kind word that changed someone's life. In an infinite multiverse, every possible version of you exists, each convinced their path is the only one, each carrying the full weight of a lived experience that feels uniquely their own. This forces us to confront the very nature of identity. What makes you you? Is it the sum total of your memories and choices? If so, then an infinity of almost you share nearly all of those. They have your childhood memories, your secret hopes, your deepest fears. They are living out the consequences of roads you did not take, becoming people you might have been. The you reading this is just one thread in a tapestry of selves, each as real and valid as the other. The universe next door holds up a mirror to our own existence and asks a haunting question about free will. If every possible decision is realized somewhere, does that make our choices less meaningful? Or does it make them more profound, knowing that each fork in the road creates not just a different future, but an entirely new world, a new consciousness branching off to live its own truth? That other you is not a phantom. They are as solid, as confused, and as hopeful as you are. They look up at the same night sky and wonder if they are alone, never suspecting that the answer is an infinity of selves, separated by the thinnest veil of quantum chance. In the end, the most staggering parallel universe may not be the one with 10 dimensions or singing stars. It is the one where your life is exactly the same, except for a single forgotten moment. It is the echo of your own existence, proving that in a cosmos of infinite possibilities, even the smallest things can birth entirely new worlds. This journey has taken us from the rigorous to the fantastical, from universes predicted by our most advanced equations to realms born from pure philosophical wonder. We have explored realities where every choice creates a new world, and others where the very laws of physics are local ordinances. We have ventured into bubbles of creation, peered into black holes that birth new cosmos, and considered the haunting possibility that our own existence might be a shadow, a simulation, or a single thread in an infinite tapestry of selves. Some of these ideas, like the inflationary multiverse or mirror matter, are testable hypotheses, predictions that future telescopes or particle colliders might one day confirm or deny. Others, like the conscious or organic universes, are profound thought experiments, stretching our imagination to its limits and forcing us to question the very nature of reality, life, and mind. Yet each one, in its own way, serves a vital purpose. They are not mere flights of fancy, but tools for thinking. By daring to conceive of what could be, we sharpen our understanding of what is. We challenge our assumptions, expose the hidden biases in our science, and open new pathways for discovery. The true value of this exploration lies not in finding a definitive answer, but in expanding the realm of the possible. So tonight, when you look up at the night sky, let your gaze carry a new kind of wonder. See not just points of light, but portals. Each star might be a window into a reality where time flows backward, or where gravity is 1,000 times stronger. The dark spaces between them could hold silent mirror galaxies or the shimmering walls of a cosmic hologram. That faint, ancient glow bathing the universe is perhaps the echo of a previous cosmic cycle, or the hum of a resonant acoustic creation. We are confined to this single, shimmering point of observation, but our minds are free to roam an infinity of might best. Which of these 25 realities resonates most deeply with you? Is it the elegant brutality of an antimatter domain, or the intimate, branching paths of the quantum you? Share your favorite universe in the comments below, and let us continue this exploration together. For more deep dives into the greatest mysteries of space, time, and existence, be sure to subscribe. The cosmos is stranger than we can suppose, and the journey to understand it has only